Good morning, sir. Myself Sagang Reddy from Mechanical Engineering, third year. Topic: Repeatability, Systematic and Random Error Corrections, Calibration Procedures, and Limitations and Fits. Introduction to Measurements Uncertainty. Accurate measurements are essential in engineering and significant applications. Understanding source of errors helps improving measurements precision and reliability. The presentation covers repeatability, error corrections, calibrate, limitations, and fits. Here we can see that in figure accuracy equals to height in first circle, precision equals to high, and in the second circle accuracy equals to low, precision equals to high. In third circle accuracy is high and precision is low. In fourth circle accuracy is low, precision is also low. What is repeatability? Repeatability refers to the degree of consistency when measuring the same item under identification conditions. It indicates the precision of measurement instruments over multiple trials. High repeatability means measurements are small, similar across repeatability tests. Source of repeatability variations. Variation in operation handles or environmental conditions can affect repeatability. Instrument stability and resolutions also influence measurement consistency. Proper procedures or controlled conditions helps improving repeatability. The types of methods are standardization procedures, control variables, calibration equipments, use multiple trials, and train professionals and use statistical tools. Systematic error explanation. Systematic errors are consist repeatable inaccuracy that skew measurements in a significant directions. They often result for calibrating issues, instruments, bias, or environmental factors. Identifying and correcting systematic errors is crucial for accurate measurements. Examples of systematic error. Zero offsets is a scale caused all measurements to be considered higher or lower. Instrument drift over time. Introduce gradual bias. Calibrate error during instruments setups can lead the systematic derivations. Here we can see that in the figure errors are also classified into two types: systematic errors and random errors. First we have to discuss about systematic errors. In systematic errors there are also two types: causes and minimizing methods. In causes, zero error, the error causes by zero error is reducing by subtracting the obtained reading from the zero error and incorrect calibrations. In minimizing methods, by improving the structure of operators. Random errors and their corrections. Random errors are unpredictable fluctuation affecting measurements accuracy. They arise for uncontrollable factors like electrical noise or environment disturbances. Statistical methods are used to analyze and minimize the impact of random errors. Here we can discuss about random errors. In random errors also there are causes and minimizing methods. In causes, parallax error incorrectly using the apparatus. Minimizing methods by repeatability taking the readings. Difference between systematic and random errors. Systematic errors cause constant bias, while random errors cause measurement scattered. Correcting systematic errors, improving accuracy, reducing random errors, enhance precision. Both types of errors are important consideration in measurement qualities. Error correction techniques. Calibration adjustment instruments to estimate systematic errors. Repeatability measurements and systematically analyze how identification and reduce random errors. Proper maintenance and environmental control minimizing both error types. Calibration procedures overview. Calibration involves comparing an instrument output against a known standard. It ensures measurement accuracy and traceability to national standards. Regular calibration is essential for reliable measurements over time. Steps in calibration procedure. Select approximate standards with known traceabilities. Perform measurements under controlled conditions. Adjust or document instruments setting to match the standards. Calibration interval and maintenance. Calibration intervals depends on usage, frequency, and environmental factors. Regular calibrations recorded maintain measurements traceabilities. Maintenance and calibrations together ensuring ongoing measurements integrally. Limitations and measurements and uncertainty. Measurement limits define the smallest and largest measurable quantities. Uncertainty quantifies the confidence intervals of measurement results. Understanding this helps in assembling measurements, reliability, and decision makings. Tolerance and limits in engineering. Tolerance specifies adaptable devices for a nominal dimensions. Limits sets the maximum and minimum precision values. Proper significance ensuring paths, fits, and functions as intended. Fits and clearance type. Fits describes the relationship between mattering paths such as clearance, interference, or transitions. Types include clearance fits, interference fits, and transition fits. Selecting approximation fits, ensuring proper assembling by operations. Types of fits here we can see that in the figure: clearance fits, transition fits, and interference fits. Types of fits in practices. Clearance fits allows easier assemble with spare of movement. Interference fits require force to assemble for a tight fitting. Transition fits provides a comparisons between clearance and interference. Choosing the correct fit, the application function required determined the suitable fit type. Factors like load, momentum, and manufacturing tolerance influence selection. Proper fitting selection prevents assembling issue and operational failures. Importance of proper calibration and limits. Accurate calibration ensures measurements stay within specific limits. Understanding limits and fits prevents parts rejection and assembling problems. Regular checks and adjustments maintain overall quantity controls. Summary and key concepts. Reliability errors, calibration and limits and interconnected in measurements quality. Correcting systematic errors and minimizing random errors, improving accuracy and precision. Proper fits and limiting selections, ensuring functional and reliable paths. particular applications and best practices, implementing regular calibration schedules and environmental conditions, using statistical tools to analyze measurements data of errors, train personnel in improving measurements and calibrate techniques. Conclusion: understanding and mapping measurement errors to virtual for quality accuracy, continuous improvement in calibration and error correction enhance reliability. Accurate measurements underpin successfully engineering, manufacturing, and significant outcomes. Thank you, sir.